Hello everyone. Welcome to this training session on exploratory data analysis using SPSS. What we will look at in this particular chapter is how is the basic normality testing different from this exploratory data analysis. We have looked at the normality in the data in our earlier session, and if at all the data is not normal, how do we transform it to make it normal, or how do we use the box plots to identify which is deviating from normal. These kind of things we have done in our earlier session, whereas in this session the focus is more on, if at all I want to identify the pattern of distribution or check out for the normality among the groups of data, not the data as a whole, not data as a whole, but by creating some kind of subgroups within the data. If I want to check out what could be the normality in each of the subgroups, or if I want to look at the descriptive statistics for each of the subgroups, this is where we can use the help of exploratory data analysis. So it can summarize the distributions across the groups, which will help me dig deeper. What do we mean by dig deeper here? As a whole, my data may be normal, but if I am trying to create the data into groups, I'm not sure about the normality in the data. So how do I ensure that the normality is present even at a subgroup level? That is what is the major intention, or probably overall when I'm looking at, there may not be many outliers in the data, but if I'm looking at it group wise or subgroup wise, there may be some kind of outliers present in the data. So that is what we are going to test as a part of our exploratory data analysis. So we can try to identify the outliers within the subgroups, not at a macro level. For this, one minimum requirement we need to look at is the way we are classifying the groups should be based on either ordinal or nominal variable. But whatever the parameter we are using for the comparison purposes, obviously the distributions or normality can be done only on a scale variable. So we are checking for the normality based on a scale variable, but the grouping of the variables should definitely be done based on the ordinal or nominal variable. For that, I'll take a very simple example, right? What is the example I can look at? This is a very simple data set I have taken, right? This is the entire list of T20 cricket innings right from 2005. 17th February 2005 was the first 2020 international match that was played. So I've collected the data right from the 17th February 2005 till the 31st August 2013, where the last 2020 international has taken place. So during this period, all I am very much all I have collected is team wise. So team wise, every match, how many overs they have played, what is the runs per over, and what was the first innings, what was their result, first or second, is it a first or second innings? So innings wise totals, this is the total runs, these are the total wickets that they have lost, and the runs per over across for each of those matches, and finally we are talking about the opponent, the ground, and whether the match was won or lost. Now in this I am creating a very simple query. I want to look at the pattern of, what is my query here? Look at the pattern of runs per over across the data. I'll look at runs per over across the data, and then I want to see the distribution or the pattern of runs per over, whether it is the same across the first innings and the second innings. That is what we are calling as dig deeper. Is it the same as the same? Is the pattern the same across the first and the second innings? That is what is the important thing we are more concerned with, right? So first let's look at it at a macro level, and then we'll take it into the micro level. Now what do we do at a macro level? Well, I'll go here. Simply I would like to see what is the pattern of RPO. This is something which we have done earlier. I can look out for the descriptive statistics using the frequency for the runs per over. I'll go into analyze, right? I may get into frequencies. I'll take the runs per over here, and I will not have the frequency tables. I can go for the statistics, but here I would like to limit the statistics only to the extent of skewness and kurtosis, and probably just the mean and the median. Fair enough. This should be sufficient for me to start off. I'll take only that. And what we are seeing is the skewness is much lesser, right? Very much close to zero. The mean and the median somewhere around this. There is a small difference existing between mean and the median, and the kurtosis is 0.73, slightly above the cutoff mark of 0.5 which we were talking about. But whatever may be the case, now my intention is not to look at the broad picture. My intention is to look at the presence of distribution and the presence of outliers within the groups of data. For that purpose, I'll use the exploratory data analysis. Now, if I have to do that exploratory data analysis, what is that we need to do? We get into this analyze, descriptive statistics. I get into explore. Explore talks about the exploratory data analysis part. Okay, we can reset first of all if there is something that is existing. And here the dependent list is the scale variable for which I want to find the pattern. I can have one or more dependent variables, but they all should be the scale variables for whom I need to find out the patterns in the data. So I will point out the runs per over here. This is one of my dependent variable, and probably if you want to test on runs, wickets and all, probably you can do the same. But just to explain the concept, I want to look at the distribution of runs per over across the innings. First innings and second innings, is the runs per over the same? And if at all there is any kind of outlier or something, I want the outlier to be identified by the case, some ID associated with the case. Otherwise, it will give me the record number. So let me leave it off. It will give me the record number. So for time being, I'll put these two things. And it is also saying, so which means here I'm grouping the runs per over based on the innings. first innings first innings runs per over is a separate group, second inning runs per over is a separate group. Now we are saying display both statistics as well as plots. We'll go with both of them. We'll look at the statistics, which are the calculations, and plots, which are the graphs. What do I select in the statistics? I'll get into the statistics part, and okay, the descriptives are anyhow selected. So basically the descriptives do contain the mean, median, and even the quartiles, the first quartile, the second quartile, the third quartile, minimum, maximum kind of calculations. Apart from that, I would also go for M-estimator and outliers. I'll talk about what these two things are. I'll go with selection of M-estimators. It is nothing but the robust estimators of the mean. Middle value estimators. There are various formulas that estimate the mean. So a tool like SPSS, even without our knowledge of formulas and all, it displays those values. So, but we need to know how to interpret them. But just M estimator is nothing but a robust estimate of the mean. And I also go with outliers. I want to see what kind of outliers are present in my both the first innings data as well as second innings data. So I would like to go for identifying the outliers also. So as part of statistics is concerned, I would be taking these particular values. All right. Then I would also look at the plot, because we want both the statistics as well as plots to be displayed. I would go for the plots also. As a part of plots, okay, there is already by default a stem and leaf plot that is selected. I could even go for a histogram because anyhow I'm looking at the normality. So I'll go for a histogram. I'll go for box plots, the box plot where the factor levels are together. So when we are saying factor levels, it is based on the factors. I'm going for a box plot, which means the various categories or the various innings. For each of the innings, a box plot is, for each of the innings runs per over, the box plot is plotted separately, one beside the other. So I would be selecting that option. Along with that, I will go for, this is one important thing for me, or probably for saying whether the data can be treated as normal distribution or not. There is something which we generally do, which is called as a normality plot along with the test. It's just not the graph. There is a statistical test that is performed which says, can I accept this particular data as normal, or is it deviating much from the normal? So by doing all these things, once whatever the analysis comes out of this exploratory data analysis, if I am able to interpret it better, it will definitely help me to assess the normality within the subgroups of the data also. So I'll do a continue, and once I run it, this is what is the output it is going to generate. Okay, now let's look at this output. Yeah, just before that, let me get back to my slide. What is that we have talked about? Let's see what all we are trying to plot here. First, let's look at the box plot. Okay, the box plot, we will go down. Right from here, we'll do all the things. We'll try to go through all whatever is being displayed. But let me start off with the box plot. The last one that is typically plotted here. Because we said factor values to be together, we are seeing this is the box plot, and we have already discussed earlier also the box plot gives us a 5 value summary. Okay, it it is allowing us to compare each of the groups. Now let's say what are the each of the groups. The dark black line which we are seeing here is the median value. Probably it is looking like the median is more or less the same or slightly higher for the first innings compared to the second innings. Then this borders talk about the 25 percentile, which is the quartile 1 as well as quartile 3. Here also quartile 1 and quartile 3. Somehow visually it is showing, it is appearing to me that the height of this box is slightly lesser than the height of this box. Fair enough. And then it is also, so that's a 25 percentile and 75 percentile. And then we call something as whiskers. This particular lines which are on both the positive side as well as the negative side, after a line, after a straight vertical line, horizontal bars that are there, we typically call them as whiskers. What are those whiskers? These are those vertical lines that end up with horizontal lines. That is the maximum limit of a statistical outlier. Anything above that line or below that line is a typical statistical outlier. And in that outliers also, there are two categories of outliers. Some of them identified with 0 or a circle, and some of them are identified with a star. In this data, what we are seeing is there are a lot of records: 181, 53, 655, 249. There are a lot of records which are identified with circles, and here also we are seeing there are a lot of points which are identified as circles, but one major point, record number 182, that is identified as a star. What does that mean? Circles are something which are treated as extreme values, or probably outliers, not extreme values. The circles are something which are treated as statistical outliers, whereas the ones which are marked with an asterisk star, they are typically extreme values and they deserve the removal as soon as possible. So they need to be given special attention. Even if possible, it is worth to go about removing these circles also, because they bias the normality in the data, right? Because of the bias in the normality in the data, probably if at all I have to do some kind of statistical test or some kind of predictions or some kind of models in the future, it becomes very difficult for me, because they make the data more and more unreliable. But at least definitely this value requires a removal compared to the outliers, but still these two are outside the scope of the statistically relevant kind of values. So that kind of an analysis. So typically if I go to my data to check out what it is, 182nd record. So how do I look at that 182nd record? I can go into edit. I say go to case. I'll ask for go to case, and in this go to case I'll specify 182. So it goes to case number 182, and what I could see is the runs per hour is 15, which is way above probably compared to the other elements in the lot. That is one of the prime reasons it is getting treated as an outlier or very extreme value in our data, which requires to be removed if at all I want to use this data as it is for any kind of future observation or the future usage. Okay, let's try to observe, let's try to go through each and every aspect and try to discuss what each of these things are. First thing it generates is a simple case processing summary. So which it is saying there are 327 records containing the first innings and 325 records containing the second innings which are valid. But there are no records where the data is missing, no issues. The RPO is not missing in any of the cases. So overall there are around I think 652 records, out of which we have the data relating to 327 for the first innings and 325 for the second innings. Fair enough. Now here it is giving me some descriptives because we have asked for some basic calculation of the descriptives. If we see, there is a descriptives that is getting computed where it is giving me the mean for the first innings 7.64, whereas the mean runs per over in the second innings comes to 7.42. So probably we can say that the mean in the first innings is slightly more than the mean in the second inning. Just to start off, right, the mean is coming something like this. Then it is also talking about the 95% confidence interval for the mean. So 95% of the times there is a 95% chance that the mean can lie only between 7.46 to 7.81, whereas here it can lie between 7.25 to 7.6. Then there is another calculation of trimmed mean, 5% trimmed mean. Means if I remove 5% of the outliers in the data, 5% of the outliers on the either side, very high and very low values, and after that compute the mean is slightly reduced from 7.64, it has come to 7.62. The same thing happened here in the second innings, it has come down to 7.39. So eliminating 5% of the values in the corners, and again recomputing the mean brought the trimmed mean to 7.62 as well as 7.39. Then similarly, the median is 7.5 versus 7.35. This is one more area to focus. The difference between the medians is just 0.15, 7.5, 7.35, 0.15, whereas the difference between the means is coming out to almost 0.3 or 0.27. Between the trimmed means, the difference is almost 0.27, whereas between the original means, the difference is almost 0.22, right? Yeah, no, 0.23, sorry. The trimmed means the difference is 0.23 and the original means the difference is almost 0.22. Whereas between the median, the difference is only 0.15, which is again an indicator that the mean is very much different from the median, right? I mean, again, when we are using the word very much, here there is a difference existing, 7.64 versus 7.5. There is a 0.14 difference, or from here there is a 0.12 difference. Here also, here the median is not much different. Trimmed mean is 7.39, whereas the median is 7.35. But look at the skewness and kurtosis. Okay, the skewness is very much close to 0. Kurtosis is also very much close to 0. Fair enough. Whereas here the skewness is 0.43. Okay, it can be treated very close to 0. But the kurtosis is pretty high, 1.47, which means there is a possibility of some extra tail when the data is not normal. Even the kurtosis is telling me here that the data is not normal. But the end thing I suggest in this, rather than looking at the numbers and saying that the data is normal or not normal, I always suggest go ahead with doing a test per normality. I'll go down in this chapter itself and I'll do a test per normality. I'll display, we'll discuss on the test per normality, from which we can clearly say whether we can accept that there is a normality in the data or there is a violation in the normality in the data. Yeah, here I would like to introduce you to one good tool, especially if I am not interested in comparing like this. If I want a simpler table, I can actually use the concept of pivot table here. Double click on this. When I am double clicking on this, I can go into this pivot and I say pivoting tray. So in this pivoting tray, what I can do is the innings, I'll drag it outside. The innings, I'm dragging it outside. Now you see the way the diagram becomes. We get a small drop down. Now this becomes more easier to look at, right? It may not help me in comparison analysis, but at least, okay, if I select the second innings in this table, I get the second innings data. I select the first innings, I get the first innings data. So pivot actually helps me in looking at the analysis in a quite simpler and in a small table kind of a perspective. Or probably I could have done something else as a part of the pivot. Okay, the same innings, right? The same innings, if I bring it to this side into the columns, I could look at a step-by-step analysis. You see here statistics 7.6, 7.4, 7.46 to 7. So this is more of a presentation. So you could very well work out on the usage of the pivot table, especially for the presentation of the data, because the default setup will do the presentation in some form, but when I'm using the pivot table, I can do the dragging of the values either into the layers or dragging it into rows into the columns or whatever is that I would like to look at to simplify the way the presentation has to be done. So that is one important aspect. So even when I am looking at the descriptive statistics between the first innings and the second innings, I am able to see that the averages as a part of the first innings are considerably higher compared to the averages in the second innings. The same way median is also slightly higher, whereas the skewness is not present that much in the first innings data, but the skewness and kurtosis are slightly more present as a part of the second innings data, right? And now the most important thing I would like to suggest here is the M-estimators. The M-estimators, what they do is there are four types of estimators that SPSS computes for us. This again, they are the various ways in which these people, Huber, Andrews, Hampel, Tukey, all these people have come up with their own mechanism to estimate the average value. From the data, they have come up with their own formulas to estimate the average values. So this is what our data has shown. This is what our data has shown as a part of those M estimators. But the interesting aspect is if we see the all these four for the first innings 7.57, 7.55, 59, 55. So basically these four people's mechanisms, they were lying somewhere between 7.55 to 7.59. So they are equally away from the median as well as the mean. They are not very close to median, they are not very close to mean. They are more or less midway between the two, right? Almost all of them 7.55 to 7.59. Median is 7.5, mean is 7.64. So all the estimators are somewhere in the middle. Whereas if you look at the second innings, 7.36, 34, 36, 34. Almost all of them are very, very close to the median. You observe the difference between these two. In case of first innings, the various estimators, the four people's mechanism of, they use some algorithm, they use some empirical mechanism with which they determine what should be the average value of the data. But what we are seeing for the first innings is all the four people's estimate is primarily somewhere in the midway between the median and the mean, whereas that is not the case in case of the second innings. All of them are very closely revolving around the median, very close to the median compared to the mean. This is one important observation for us. The more the various estimators are closer to the median compared to the mean, there is a possibility of the data not adhering to the normal. We have to again do some more tests on it, but at the sight of it, I should be able to say that my distribution is more or less not normal. So if the estimates are close to the median than to the mean, we can very well make an assumption that the data is not much normal. So what we have typically seen in this case is the median, the estimators, the four types of M-estimators, especially for the second innings, they are very close to the median compared to the mean. So there is some doubt in my mind that there is a possibility that the data is not normal. We have to still further go down to check out whether that is the reality or not. Okay, let's go down. Then one more output which SPSS gives for us in this scenario is the outliers or the extreme values. Generally what it gives is the top 5 and the bottom 5. So when I look at the runs per over in the first innings, the highest value was 13, and probably the fifth highest value was 11.14. But you see, with respect to the second innings, there is a highest value of 15, but the lowest is still 11.47. This is again, there is a big gap. In case of first innings, you don't see two big gaps at any layer. 1 versus 2, 2 versus 3, 3 versus 4, or 4 versus 5. You don't see too much of big gap. Whereas what you see in case of second innings is there's a big gap between the highest and the second highest runs per over. 15 to 12.17. So it's almost a 3-point difference. So that is what is contributing to the very low, very high deviation from normality. Similarly, you look at the lowest 5, 3.5, 3.7, 3.8, 4.2, 4.3. Again, not too much of a big difference. Even in the second innings, you don't see that much of a big difference. 3, 3.4, 3.7. So on the downward side, you don't see too many extreme values being present. But on the upward side, we are able to see the presence of some extreme values. So that is again only majorly in the second innings we are able to observe that pattern. Of course, there is something in the first innings also, but more clearly it is evident as a part of the second innings. The next one is the real test for us. The real test is the test of normality. Let's go back to our slide and try to understand what it is. It is the overlay of, this is the overlay of a normal curve on the actual data. A normal curve is fitted on the top of the actual data to assess how much is the consistency existing between the actual data and the superimposed normal curve on the top of that. The more the fitment is, you will see that the significant levels will be much greater than 0.05. So for that test, what you will see is if the significance level is less than 0.05, we say that the fitment is better, good fitment, which means your data can very well be considered as normal. But wherever we are seeing that the value is 0.05, greater than 0.05, the fitment is good and there is a normality. But if it is less than 0.05, I can very well say that the fitment is bad and it is not normal. There is a deviation. So basically it goes with this kind of a hypothesis. The null hypothesis here simply says the actual data is equal to fitted data. And the alternate hypothesis goes with actual data is very much deviating from the fitted data. Now, we'll be seeing in various other hypothesis testing mechanisms also, when we see that the significance level is less than 0.05, we will typically go with the alternate hypothesis. So the alternate hypothesis here suggests that your data is not normal because actual is not the same as the fitted. Means actual is not the same as normal. So we can very well conclude that my actual data is away from normal. But if it is greater than 0.05, I generally don't go with the alternate hypothesis. I may go ahead with the null hypothesis itself, wherein I will mention that my actual is more or less replicating the fitted data, which means actual and normal more or less are the same. So when I go back to the data to look at it, in the first innings, the significance level, there are again two mechanisms which SPSS uses to test this normality. One is called as a Kolmogorov-Smirnov test. The other is called as a Shapiro-Wilkie test. And both these tests, they go with the simple understanding that, so even if I don't know how I have calculated all these things, it is straightforward for us. Look at the significance levels, 0.20, 0.18. If they are greater than 0.05, I can go with the null hypothesis, which means the actual distribution is more or less same as the normal distribution. Whereas in the second case, okay, here it is greater than 0.05, but here it is much lesser, 0.001. So this is what will give me some kind of an indication, probably some kind of a doubt for me to say there is a possibility that the second innings data is not that much normal. As per this, I don't have too much of an evidence, but as per Shapiro-Wilkie, I am able to conclude that there is a too much of difference between the actual data and the fitted normal distributed data. So probably if I have to make one statement going with the Shapiro-Wilkie test, I can very well make out that there is not much of a normality in the data going ahead with the second innings data in the runs per over segment, right? So that is the way we conclude whether our data is having normality or not. Now when we look at the graphs, Okay, you can look at the histograms which talk about the normality. We have discussed them earlier. So this is looking more and more like a normal chart. Whereas here there are some extreme values. Probably this is the number that is impacting your normality very badly. If this has been removed and the same test is rerun, it may be very much possible that we may look out for the normality in the data. The same thing is being done by your stem and leaf plot. It is nothing but, this is one good chart. It takes your all original datas and plots them. So it's basically like, okay, 3.5, 3.7, 3.8, 4.2, 4.3, 4.4, 4.4. This is the way it tries to plot your entire data. And once you look at it from the opposite direction, from the left, you see some kind of a pattern in the data. You try to join the corners, you see some kind of pattern in the data. So that is also another mechanism through which I can look at the normality in the chart. I can look at the normality in the chart even through the stem and leaf chart. The only advantage, or probably the major advantage which I could see with a stem and leaf plot, is it plots based on the original data. It uses the original data values to display the distribution shape. This is what is represented by stem and leaf plot. So the 3, if I have a number called 3.8, 3 is shown in the stem, zero point 0.8 is shown in the leaf. So basically it's like 3.8 is occurring 2 times, 3.9 is occurring 1 time, and so on. This is what is the representation of the shape of the stem and leaf plot, from which we can again assess the representation of the normality in the data. And there is a legend here, stem width is 1, each leaf is one single case itself. There is one more way we look at the plot, which is called as QQ plot, quintile plot, which is again a test of normality of the data. That if the data is more and more normal, we need to have the observed values. We need to have the observed value, the graph between the observed value and the expected normal. So if at all my whole data has been normal, all these actual points should be on this straight line itself. The more the actual points are closer to the straight line, the more normal is my data. Very few points deviating, that too by very small amount, indicates heavy normality in the data. So these are visual representations of whether the data is more normal or not. In the first innings, this is the small deviations that were existing, whereas in most of the cases, all these points are very much lying on the normal curve itself. Whereas when we look at the second innings, yes, most of them are lying very close to the normal curve, but the big issue is somewhere here. There is a huge deviation of this one single point from the normal straight line. That is one of the reasons the whole thing is coming out as a deviation from normality. If I take care of this one single point by eliminating the outlier, probably my issue is resolved to a large extent, right? The same thing we can look at the detrended normal curve, which will talk about on an average what is the deviation of each of the points from the normal. Hardly 0.2 units, and this side also not too much, very small deviations from the normal. Only these points are very widely deviating from the normal, and that too by the extent of zero point 0.6 units. Whereas if we look at in the second innings, okay, again most of them are deviating not more than 0.3, 0.4 units. but this is the big culprit. It is deviating by almost 2 units from the normal, and that is one of the prime reasons our entire analysis is coming out that the whole distribution may not be a normal distribution at all. So if I typically handle that one single instance, how do I handle that one single instance? I have discussed it earlier. Very well we can very well remove that particular record. I can say I'll get into data select cases. In that select cases, I'll use a simple condition. If the runs per over is less than 13 or something, use only those records where runs per over is less than 13. And with that exercise, if I rerun this entire explore, probably the whole problem would be rectified and both of them would go more or less normal for me. Let's quickly go down and look at the scenarios. Right now, the mean and the medians. Okay, look at these estimates now, or probably it's better that we look at the tests. Yeah, both of them are now showing greater than 0.05. That's an indication that both of them now can be very much considered as a normal. And if I'm coming back, let's say to the normality plot, right, detrended normality plot, the maximum difference is shown to the extent of zero point 0.5 units. The same logic if I'm coming back for the second one also, the maximum deviation again is being shown to the extent of 0 0.3, 0.4 units. So now this is more or less normal, and probably here we are seeing hardly three or four three or four elements here which are circles, but there is no star, which is not many outliers are being present in my data. Now with that single simple analysis, I can very much make out that now not only the entire data is normal, entire runs per over for the entire data is normal, but I can also assume that by dividing the data into subgroups, the first innings and the second innings subgroups, I can very well say that both the subgroups also independently are following a normal distribution. All right. So you can try out on your data. All these you can try to break down based on some other parameter also now. And based on that, check out whether your data is more normal or not. But now, if this basic understanding is clear, not just observing the skewness and kurtosis to talk about or test about the normality in the data, but we also use a normal distribution test to assess the normality, right? So this is what I would like to convey to you as a part of this chapter. If you have any further queries on this, I suggest that you feel free to give me a call on this number 98480 or you can even send in an email to me at this email address vamsidhar@pacegurus.com, and I can get back to you with the relevant resolution for your queries. Thanks a lot for listening to this session. Thank you very much.